want to have 24s as a product, or 24 or 1 over 24. Now to obtain that gives me psi 1. To obtain psi 2, then I will have to take such a function. Look, please. So I will take such a load, and this response W will be psi 2. If I want psi 3, then I should take quadratic function here. So this is what? Alpha times psi. Here will be alpha times psi square, etc. This allows me to obtain various functions. Any questions? Yeah, accuracy. Question was asked about accuracy. Generally speaking, Galerkin method has a good accuracy. Sometimes extremely good accuracy. Say, paying attention today, for example, we did see even in one term approximation. So naturally, more terms we take, that should be a better approximation. But even in one term, look, instead of 97,409, we obtain 97,548. So actually, in the third digit, the difference was. But if we take two-term approximation, then approximation for the first frequency will be much better. A rule of thumb, if I want to have first 10 frequencies accurately, I should take 20 terms, 2 times more. Why? Because at the very end, maybe its accuracy is disturbed or perturbed. We are not getting that much accuracy. If I would like first 10 frequencies to be obtained accurately, I need to use 20 terms. You may say, why in the world I may need 10 frequencies? Is it not enough to use first frequency? It happens that, for example, in some cases, extremely many frequencies are excited. For example, the wing of Concorde, when it flies, say, when it flew, I must say, overseas, so from England to New York, so there are several hundred natural frequencies are excited. So we would like to find several hundred natural frequencies, not just 10 natural frequencies. Then accuracy is even, accuracy that is needed there is even higher. Yes, in that case, Galerkin method already will be inapplicable. We need to use some other methods. Especially, there are some frequencies. So for example, what immediately comes in mind to use some asymptotic methods, because asymptotically, for a very high frequency, beams behave the same whether they are simply supported or clamped. Simply supported frequency is J times or K times pi, yes? K pi. K's frequency is K pi in force power. But if it is clamped, then it will be K plus 1/2 times pi. You remember? So K plus 1/2, so that is almost like, I mean, for a very big K, this is 500. 500 in force power and 500.5 in force power is almost the same from calculation point of view. So very high frequencies, the wing of Concorde does not feel the boundaries, because these are like, if we can say, old person, local wrinkles, because there are many, many, many waves. So what is interesting is what happens here in this place. And what happens here is not influenced what happens very far away at the boundaries. Boundaries are as if not that important. Boundaries are like very far away. Like if there is a small fly there sitting in the middle, he does not see the end, does not see the boundary. Is that, I mean, I'm talking in metaphors, but that is what happens mathematically. If it is clamped free, if you remember, then it is j plus 1 force, and then in force power, etc. So for high natural frequencies, so one can use some asymptotic methods that are taking into account that they are not influenced by boundaries or very little influenced by boundaries. Any other questions? So I brought you an example of Concorde. That I know that is what happens there. Or what happens there, because Concorde does not fly anymore. But I'm sure that humankind will not rest and spend 12 or 14 hours of flying from New York to Tokyo. Humankind will need probably to have a faster airplane that gets there in 2 hours maybe. Okay, if there are no questions, we will assign one more homework. But I have to find first the pay is homework. Homework 15D. So take a simply supported beam that is, say, like this, that is alpha psi in n minus force power. So n is greater or equal than 4. So we have the differential equation EI, etc. Then we have psi n in force power equals alpha psi n minus 4. Yeah. So here then psi equals 0, psi equals 1, okay, because psi equals x over L. And find psi n. Psi. Find general expression. Find general expression for it. So it's very easy problem. Of course, you integrate once, integrate second time, third time, 4 times, and satisfy boundary conditions each time. Is it not? We have to satisfy 4 boundary conditions. Psi at 0 equals 0, psi n second derivative equals 0. Then psi n at 1 equals 0, psi n second derivative at 1 equals 0. Okay, there are these 4 boundary conditions. Yes. Did we write this? Now I would like to ask you some. I did not check yet the test. Did not complete. But one or two students asked me already, maybe unjustifiably, I don't know, because there are no grades yet, whether or not we could do something that is called retake or second approximation. Do you think that we need to have a retake? No? You could use, okay. So we will see then. We will see how. I will inform you next time. I will have already the grades, because I checked sporadically. Some people, at some students I checked first problem, in some other students checked second problem, but I did not check, so to say. I like to spread. I don't like to concentrate on one student, so I like to check one problem, then second problem somewhere else, and by this means check is more objective. That is my experience shows that it is not good to check first student and second student, etc., because anyways one cannot finish, and therefore it takes anyway several days, and maybe the checking at different days maybe has some influence. I don't know. I have no idea. But because I never do that, I never check in different days. Therefore, I try to check in one day something and then second day something else, etc. Okay, if we will see, and then we will discuss that next time. Any other questions? Yes.
Earlier you said that the Galerkin method causes an overestimate.
Yes, overestimate. Okay, because I think that I try to answer this. At least the explanation is that we are as if, I mean, okay, W should be behaving in a certain manner, exact W. But I actually make this W a bit different. So this is like as if I know the exact W. But then I'm slightly changing that exact W. So as a result, as if I'm imposing additional constraint on the beam, that it should deflect in a certain manner. And if you remember, in 1 degree of freedom system, we had omega square equals k divided by m. So adding constraint is like increasing stiffness. Omega square k is in the numerator. So therefore, instead of regular k, I, as it were, increased this k. Because I increased this k, I got a bigger natural frequency.
Why wouldn't you increase it?
Okay. It was never observed that it was decreased. Because you always, look, there is always exact solution, which we do not. Okay, by the way, it will never increase, but if you will put exact solutions there, for example, for simply supported beam, and someone did, I mean, in the homework also I did not ask, he said psi 1 equals sine pi x over L. That is an exact solution. If you do Galerkin method by sine pi x over L, you will get exact solution. So Galerkin method gives exact solution if you put exact psi. But if you don't put exact psi, that means that, pay attention, this psi, it is not sine function, this psi minus 2 psi cubed plus psi in fourth power slightly differs from sine function. This difference actually, we say that you don't behave like this, your displacement is different. But that means that I as if imposed some constraint on the beam. I told him how to behave. Look, please, when you tell to a person, do this and this and this and this, he becomes very stiff. Just because he does not naturally like this. Sometimes could be that he loves it, and whatever you tell him, I never met such people. But maybe there are such cases that they are anticipating. Maybe, you know, an emperor and slave relationship. Maybe there is something like that. Okay? But even from biblical stories, we saw that humans, you know, we did not listen. Even when we had an interaction with Highest authority, we did not listen. So there is some stiffness in the system. I don't want to continue because this is recorded, so I don't want to continue the discussion in that direction. Any other comments? Now, there are other methods. Okay, someone may say the following. Fine, the exact solution, imagine, is 10. Natural frequency is 10. Imagine. So I will use Galerkin method and I will get 11. Fine. But imagine the excitation frequency is, say, now there is some excitation frequency. I know that if excitation frequency equals 10, then naturally there is a resonance. But now I'm actually saying that my estimate is 11, not 10. Then I'm saying that actually if excitation frequency is 11, then I'm getting the resonance. So actually this is wrong. So I therefore may want to find another estimate which gives me a lower bound of natural frequency. Then I would say that natural frequency lies, say, between 9 and 11. Okay? So there are such methods that give something that is lower bound approximations. So there are something like temple inequalities and Collatz inequality, etc., etc. So there are such methods also that give lower bounds. But good thing about Galerkin method is that, yes, psi, just using one term is a question. One term is also good. Why? Because sometimes I'm solving problem with finite element method. Finite element method means that I put some numbers and I'm getting some numbers and I don't know whether these numbers make sense or not. So then it is good to use one term Galerkin approximation to get at least, do my numbers that I'm getting from the computer correlate, do these numbers correlate at least with my one term approximation? Am I in the same ballpark or not? Or maybe I just put wrong data there. So one term approximation, still it is good to see whether you are going into right direction. But if you will take more term approximations, then you are getting very good results, extremely good results. Say, the best results that have been reported are one American scientist, Lissa, L-E-I-S-S. He used 36 terms, 36 terms of approximation, and capital N equals 36. Naturally, he could not do it by himself. He had 3 or 4 graduate students, and that was done a long time ago. I mean, that was done maybe 20 years ago or 25 years ago. But he obtained extremely good approximations with, 36 mode shapes, which is naturally lot of work. The students probably 3 or 4 doctorates they get at that time. Now, naturally, no one can get doctoral degree for Galerkin method for the beam or for the plate or something like that. That is done already. There is finite element method approximations, etc. You have some question? No. What has happened? Say it again? No. Mr. Dale, you have any question? No. Mr. Peguero? Okay, invent a question. You have any questions, sir? No. What about yourself? Okay, so there are other approximate methods also, like Rayleigh, Lord Rayleigh, in 19th century, derived some other method. It's called Rayleigh's method. We will deal with that. Then there is Ritz, Walter Ritz, German mathematician. Both Rayleigh and Ritz obtained Nobel Prizes, but not for vibrations, for something else in physics. But they dealt with vibrations a lot in the beginning of past century, actually. Okay, if there are no more questions, we will finish the class and we will meet on Wednesday. Have a good day.